All right, so first half of the class behind us. First half of the class really focused on this tabular approach to analyzing the relationship between two categorical variables, allowing us to potentially adjust for, right, a third or a fourth or a fifth type variable. Very powerful approach. Tables in and of themselves are probably one of the most powerful sort of descriptive statistics, right? So even when we do other approaches, for example, logistic regression, when we're trying to summarize our data, we still will often go back to a table, right? A picture speaks 1,000 words, and a table speaks even more yet. However, from an analytical standpoint, there's something perhaps even a bit more powerful, and that's what we're going to spend the second half of this class talking about, this idea of what's referred to as logistic regression. So logistic regression is a statistical technique that allows us to model how a dichotomous variable, right? So dichotomous, remember, means just two possible outcomes. A dichotomous variable y depends on any number of explanatory variables. And not just any number, but any type of explanatory variable. So that is really expanding what we've been able to do, right? Now, admittedly, there's still a little bit of a restriction. A little bit of that restriction is that our y variable can only take two values, although we will eventually see ways of loosening up that restriction. But for now, kind of plain, ordinary, vanilla logistic regression, we just have a y that takes two values. That is a bit restrictive. But our x's can be anything, which is not something that we had in our table approach, right? That is, we could not put something like BMI as an explanatory variable in our table approach because, right, being able to put these rows and columns, not really possible if we're working with some kind of variable that's, right, ultimately or potentially continuous. So what are some examples for logistic regression? We might, right, from a sort of medical perspective, this is kind of like a classical example used a lot in textbooks. We might want to model whether or not a baby's birth, premature or not, depends upon whether or not the mother smokes. That's just another way of doing a 2x2 table right there, right? But, right, more interesting, right, something we haven't learned how to do yet, we might model how coronary heart disease, yes or no, might depend upon a person's age, right, a continuous variable. We might also be interested in modeling whether or not someone defaults on their credit card. So credit card companies, banks use logistic regression modeling a lot because they're often looking at things like, was a marketing campaign successful, yes or no? Is someone going to default on this particular credit card or loan, yes or no? We might model that as a function of their credit rating, something that, again, we cannot do with tables. So here's just kind of scratching the surface of the really cool, really awesome, really powerful stuff that we're going to be able to do with logistic regression. Or why not, to continue our trend of spiritually depressing, disheartening examples that seem to be the centerpieces of this class. We could also use it, as we'll see in a kind of exploratory exercise, a lab, we could use it to predict the fatal consequences of the ill-fated 1986 Challenger space shuttle launch. So a lot of us might be a little young to remember that. I mean, I myself was only 11 years old, but I mean, it was profound enough that, right, even at 11, kind of I carry it with me, to this day. If it's not something you're aware of, right, I encourage you to take a look at the Wikipedia article. And then in the lab, we'll kind of go a little deeper about how maybe sadly they could have used logistic regression and maybe anticipate, what unfortunately happened. So what is logistic regression extending? Well, first off, it's obviously extending 512 by allowing our y variable to be decidedly non-normal, right? About as non-normal as you can get. It extends our work with tables, as we've already mentioned, by allowing the use of any number of explanatory variables, as well as allowing continuous covariates and explicitly quantifying relationships of interest. So let's look a little bit more closely at how it extends 512. So we could kind of look at 512 maybe a little bit different than we did previously. This is actually paving the way of something called a generalized linear model, which is like a really nice, powerful kind of umbrella type way to look at a whole bunch of different modeling techniques or an infinite number of modeling possibilities. So we could rephrase some of our assumptions in 512 in the following way, and so hopefully this makes sense. I know it's not quite how we expressed it, but hopefully you can see that this is equivalent to how we expressed it. And if you can't see the equivalence, don't settle for not knowing. This is something that should make sense to you. If it doesn't make sense, there's a disconnect somewhere that needs to be fixed. So reach out to me, reach out to some graduate assistants, right, and talk about this further. But in 512, we might say the following thing. We might say that our response variable y follows a normal distribution. All right, that's our normality assumption, with a variance sigma squared. That sigma squared doesn't have a subscript I, so that's our homogeneity assumption. Doesn't depend on any explanatory variables. And a mean that is a function of explanatory variables, right? So that's functional notation. The mean is a function of x. It looks like a bar, but if you kind of squint at it, it's actually a little bit of an arrow. That arrow denotes a vector. So a vector just means a collection. So putting that x with that bar over it is just shorthand notation for saying a collection of explanatory variables. So we're saying that the mean mu is a function of some collection of explanatory variables, and in particular, that function is that linear combination that we're used to seeing, right? So what are we doing? And this is a more general way of trying to model some random phenomenon. Is one, we look at the random phenomenon itself, y, and we say, what distribution do I think it follows, or what distribution do I want to attempt to model? In 512, we're trying to model a normal distribution. Then you think to yourself, okay, for this distribution, what are the different parameters, right? We know from 505 that all these distributions have different parameters. And then we start thinking, okay, in what way are these parameters functions of other variables? In 512, we say that the variance, that's one of our parameters, doesn't depend on the explanatory variables at all. However, our mean is a linear combination of explanatory variables. Now, right, that's the heart of kind of what I want to get at. I will point out, right, that there is also this extra assumption that y itself, so the mean of y is this linear combination, but y itself is this linear combination plus this error term, right? And then our error terms have a mean of 0 and are independent of one another. So that's kind of, I didn't make it explicit here, but there still is, of course, that independence assumption as well. So yeah, so more generally, we assume some particular distribution. In 512, that was a normal distribution, and then we model one or more of that distribution's parameters as a often linear combination of explanatory variables. Now, how might we adapt that way of looking at the world? How might we adapt that way of modeling to the type of situation that we're trying to cope with now? Well, imagine we have a dichotomous random variable. What is its distribution? A dichotomous random variable, a random variable that only takes one of two outcomes. We call that mathematically, we call that a Bernoulli random variable. If you haven't taken 505, you could look it up. Very simple, very straightforward. Just that's its definition right there. A Bernoulli random variable is a random variable that takes just one of two outcomes, often generically referred to as a success or a failure. Whatever outcome we label as a success, then our parameter of interest is the probability of that outcome, the probability of a success, which we call pi. So that's what we have to deal with. And so we want to look at the situation where this pi might be a function of other explanatory variables, right? So maybe y is whether or not you're going to default on a loan, and pi is the probability of defaulting, but that probability of defaulting is maybe a function of a bunch of other things. The probability of defaulting is maybe a function of whether you've defaulted on a previous loan, whether or not you're currently employed, what your average salary is, how old you are, your credit rating. That is, it could be a function of a whole bunch of different variables. And the more variables we know, the more accurately for a given person we might be able to assess, right, the true probability that that person will default on their loan. So our question then becomes, okay, right, I have this random phenomenon, yes or no. I want to model the probability of this phenomenon happening, and I want to model it as a function of explanatory variables. How? How do I do that? This would probably be our first guess, right? This would be what we would be tempted to try, but what's wrong with that? What's wrong with this in a sort of at least strict mathematical sense? Exactly. The bounds of that equality do not necessarily match up, agreed? The left-hand side is a probability. Probabilities are always, without exception, between 0 and 1. The right-hand side, for certain explanatory variables, right, continuous ones, for example, and certain values of those things, could in theory take any value from negative infinity to infinity. So the bounds of the left-hand side of our inequality do not match with those on the right-hand side of our, or sorry, not of our inequality, of our equality. The bounds of our left-hand side do not match the bounds on our right-hand side. Yeah, so as I just said. So we have a problem. So we have to be creative in terms of overcoming it. We have to be creative in terms of fixing it. Well, what about this? So the left-hand side, what's that? That's odds, right? We learned that, I think, first day of class. So what if instead of modeling the probability of something occurring, we model the odds of something occurring? What do you think about that? Does that fix our problem? It's not entirely fixed, but you might argue it's a little bit better, right? So our right-hand side is still technically unbounded. Our left-hand side is what? Our left-hand side is now bounded from 0 to infinity. Do we see that? Neither of those numbers can be negative in the top or the bottom. Our numerator can't be negative. Our denominator can't be negative. So that left-hand side can't be negative. And in theory, it could go to infinity, right? So, right, if this was like 99%, we would have 0.99 over 0.01. So I guess that would be what? That would be 99, right? Or we could have, right, 0.999 over 0.0001 and so on and so forth. So we can make that thing, right, as that numerator gets closer and closer and closer to 1, that left-hand side is getting arbitrarily large. So, right, it's better. We've kind of loosened up, kind of stretched it out to kind of encompass the right-hand side of the number line, but it's still not possible for it to take negative values. So at least, right, in the general sense, it's possible for that right-hand side, come up with examples where that right-hand side might be negative, but it's impossible for that left-hand side to ever be negative. So, ta-da! Voila! So, third time's a charm. Our logistic regression model is this thing right here. It looks a little crazy at first blush. Whatever the heck first blush means. It's the log of pi over 1 minus pi. So it's the log of the odds. This particular function has a name. This particular function is referred to as the logit function. So the logit function for some input pi is the log of that input over 1 minus the input. When we're working with probabilities as our input, we could just say, well, it's the log of the odds. Log odds, we often say. Now, it should be apparent to us that now the left-hand side does take values from negative infinity to infinity. So sometimes if you just dive right into a logistic regression model and you have this kind of crazy thing on the left-hand side, the log of pi over 1 minus pi, like what's going on with the katha? Well, of course, it has to be that. It has to be this so that the left-hand side has the same bounds as the right-hand side, right? Because the log can be negative, agreed? Typically, I wrote it like generically log, but often we're doing like log base e. So, right, e to the 0 is 1. So the log of anything less than 1 is going to be a negative number. Hopefully we're familiar with logs and exponentiating. If not, again, feel free to reach out to me. Feel free to reach out to a GA. Play around with it in a calculator, right? Take the log of 0. Take the log of 1 and see that it's 0. And then take the log of something between 0 and 1 and see that it is in fact a negative number. And as you take the log of something closer and closer and closer to 0, you'll see that that log of that number is going right further and further and further out, kind of getting arbitrarily large in the negative direction. And so now, it's like Goldilocks. The bounds on our left-hand side are just right. So that's our equation that we're going to work with, where unfortunately the probability is what we're interested in, but because probabilities are between 0 and 1, we have to kind of work with this complicated function of the probabilities. And so instead of modeling the probabilities as this linear combination, we model the log odds as this linear combination. However, we will at the end of the day want to be able to talk about probabilities, which means that we need to be able to kind of unravel, decomplicate this function. And so that's what we're going to look at in the next couple slides. And that's going to require a little bit of notation. So to kind of make our life a little bit easier, let's use that delta symbol as just a shorthand notation for a linear combination of x's. So delta is just that usual linear combination of x's. And in situations, right, in reality, we won't know the true betas. So in reality, we're going to have to estimate them. And so that'll give us, of course, our estimate delta hat. So this should be very straightforward to us. This should be very, very evident, the top point. We could find the odds that y equals 1 for a given set of covariates, where we go back to that logistic regression equation and we just exponentiate both sides, right? So the odds, so we can solve for the odds of something occurring. The odds of something occurring are just e to that linear combination of explanatory variables. Now, again, it is just basic algebra to kind of go and solve that further, so it might be a fun little exercise for you to try on your own. You could further algebraically move those numbers around to solve for pi. if you solve for pi, you can show that the probability for a given set of covariates is e to the delta over 1 plus e to the delta. So we can solve, once we have that equation, once we've fit that equation, we can exponentiate it to get odds, and then we could take that exponentiated thing and put it over 1 plus that same thing to solve for actual probabilities. So let's look at an example to make this notation, to get a little bit more comfortable with the notation, and then from there we'll actually talk about how to analyze this example with kind of a toy data set using SAS. So we wish to see whether or not disease status, present or absent, depends on smoking status, yes or no, and gender. So, right, our y variable is disease status, right? Only takes 2 outcomes. As of now, it has to. We don't have the ability to make that y variable anything more than 2 outcomes. And we have 2 x variables, smoking, yes or no, and sex, male or female. So there's our 2 variables. We'll say x1 equals 1 if male, 0 if female. We'll say x2 equals 1 if smoker, 0 if non-smoker. Right, so dummy variables. So we have 4 possibilities, right? You could be a male smoker, a male non-smoker. You could be a female smoker, female non-smoker. So we have 4 outcomes, and so, right, we have the probability for 4 of these outcomes, right? So for any one of these 4 outcomes, what's the probability of that person getting our disease? Right, so let's say that pi 0, 0 is the probability a female non-smoker gets the disease. Let's say pi 1, 0 is the probability a male non-smoker gets the disease. Here I intentionally left those other 2 blank, so why don't you pause the video and write down, or at least think to yourselves, what those other 2 probabilities are. I guess I don't have to just sit here quietly since you've paused it, so I can just go straight and say it myself. So that pi 0, 1 is going to be the probability a female smoker gets the disease, and then pi 1, 1 is the probability a male smoker gets the disease. And so our regression model will be logit pi ij. Right, so that ij is now indicating, right, how this probability depends upon our x's. 2 x's, so I just kind of denoted that with 2 subscripts. It's this beta naught plus beta 1 x1 plus beta 2 x2. And since x1 and x2 are dummy variables, right, we can go ahead and solve for these different things. So, right, the logit of pi 0, 0 is, right, a female non-smoker, so we plug 0 in for x1, 0 in for x2. Those 0 out, we have just beta naught. Logit pi 0, 1, what would that be? I think that's a female smoker, is beta naught plus beta 2. Logit pi 1, 0 is a male non-smoker, so what's that going to be? Go ahead and pause it. Write it down, think about it. Unpause. That's going to be beta naught plus beta 1. And then the last one's going to be beta naught plus beta 1 plus beta 2, right? You should be able to see that. Again, I know sometimes, like I talk about like a Poisson distribution, and I say, if you haven't had 505, don't worry about it. But this is definitely something, I don't care if you've had 505 or not. This needs to make sense to you. And if you're not seeing it, that's a problem. And then you need to reach out to someone, probably me, to talk it over and kind of build these connections. So our overall model equation, we've already said this, has these 4 special cases. Right? We have 2 possibilities for sex, 2 possibilities for smoking status. So more generally, these combinations of explanatory variables are referred to as covariate patterns. So we say in this example, we have 4 covariate patterns, which means that there's ultimately potentially four different probabilities that we need to model. Now, if we want to model the odds for each of these 4 covariate patterns, all we have to do is exponentiate. So we already said, right, for example, the log odds for female non-smokers is beta naught. So that means the actual odds are e to the beta naught. And so on for the other 3 possible covariate patterns. Similarly, from the formulas that we had earlier in the lecture, we can solve for probabilities. So if we wanted to solve for the probability, that's 0, 0, so the probability that a female non-smoker has our disease of interest, well, that's just going to be e to the beta naught over 1 plus e to the beta naught. If we want to know the probability that a female smoker has the disease of interest, that's going to be e to the beta naught plus beta 2 over 1 plus e to the beta naught plus beta 2, and so on and so forth. So we have odds, we have probabilities. What is something else that we've talked about before? In fact, we talked about this as like a really nice way of showcasing possible relationships when we're working particularly with categorical variables, and that is an odds ratio. So what if we wanted to compare the odds of disease for males to that of females? Well, we know that we could do that with an odds ratio. But how do we make that odds ratio? Well, we know how to make odds, right? It's just the odds of one over the odds of the other. And we saw how to compute those odds in the previous slides. The wrinkle, right, and it's a very minor wrinkle, is that we can't do odds of just males, right? Because we either have to specify a male smoker or a male non-smoker. Does that matter? Does that not matter? I don't know. Let's explore it and kind of try to think it through. And let's start our exploration by looking at the odds ratio of male smokers versus female smokers. So at least that's comparing apples to apples, right? And then we'll do an odds ratio of male non-smokers to female non-smokers. That's oranges to oranges. And then we'll see what that looks like and then kind of go from there. So we have male smokers on top. So go back to your previous slide. And so we have male smokers. It does look like our second variable was a smoking variable. And then we have female smokers on the bottom. So I just took those values from that previous slide. It's just the odds of a male smoker on top, the odds of a female smoker on the bottom, and then algebraically, just through a property of exponents, that simplifies to e to the beta 1. Now let's do this for non-smokers. The odds ratio of males to females when we're focusing on non-smokers is, again, the odds of a male non-smoker. The odds of a male non-smoker getting our disease are e to the beta naught plus beta 1. The odds of a female non-smoker are e to the beta naught. That algebraically simplifies to e to the beta 1. That's the same answer as before. So, what do we observe? We observe it doesn't matter which situation we focus on, right? The odds ratio for males to females, as long as we're comparing like to like, is going to be e to the beta 1. Beta 1 is the coefficient for our sex variable. So what that means, which is kind of cool, is that we could take our coefficient for our sex variable, exponentiate it, and get an odds ratio. That's very nice. So that means that that coefficient is not necessarily directly interpretable, but if we exponentiate it, it does end up having a nice interpretation. Yeah, so as long as we're willing to assume there's no interaction, right? That's essentially what we're doing between gender and smoking status, and our current model does not have interaction in it, then both methods are going to lead to the same answer. And then I leave it to you, right? Again, because we learn by doing, not by watching. I'll leave it to you to verify that the odds ratio of smoker to non-smoker is going to be e to the beta 2. So that's your exercise, and it's up to you to hold yourself accountable to stop this slide, to pause this slide, and derive that value right there. So that shows us like all the different theoretical equations, and those are all well and good, but of course, right, the reality is these are conjectured theoretical relationships, but those of us living, right, in the dirty trenches of day-to-day life do not know what these loftier Platonic parameters are. What we need to do is instead gather data, look at that data and use that data to come up with best estimates for these betas, which could then be used to estimate odds, probabilities, and odds ratios using the formulas that we just talked about. Now, how do we do that? We do it by asking someone else to do it for us, right? Lazy person solution. We do it by asking SAS to generate these best guesses. These statistics will become our beta hats, and then we can replace all the betas in our previous formula with beta hats to come up with our needed estimates. So here's some fabricated data for our generic disease. So we have disease, we have our sex variable, our smoking variable, and so I plug all that in there. A new proc, so here's our new proc. So how do we do logistic regression? We use something called proc logistics. It has a data step, just like almost all of our procs do. It has a model statement like we're used to using from 512. Y variable on the left, as many X variables as we would like on the right. Because I entered my data set in that compact way, I have to communicate that to SAS. I do that in proc logistic with a freak statement. So the freak statement specifies a variable. Here I'm calling that variable count, and it counts how many observations we have for each possible covariate pattern. Okay? The last is the descending option. So that's actually overriding a default. The default is ascending. What is that controlling? It's actually controlling what we're going to model the probability of. SAS's default is to model the probability of the lower outcome. So the 0 is what it would model, right, by default. And so if I want to override that, I use the descending option instead. So the ascending option would have modeled the probability that y equals 0, the probability of not getting the disease, but probably we're more interested in the probability of getting the disease. So I have to specify that with the descending option. We'll see other ways of specifying that in SAS down the road. So here's my output. We'll kind of talk it through. We could look at a few pieces of it right now. First, look at that response profile. So response profile is focusing on our Y. And so it tells us a little bit of kind of summary information. It tells us that, right, we have 45 people with an outcome of 1. So 45 of the 75 people in our data set, 45 have the disease, 30 do not. Now, very critical is that line underneath it. I would suggest every time you run proc logistic, read that line there. Because it's very, very easy to accidentally model the opposite of what you intend to model. So there it says probability modeled is disease equal to 1. Try running it yourself, right? You have the actual data set and the code in the previous slide. Try running it yourself without that descending option, and you will see that what SAS says is the probability modeled is disease equals 0, right? It's very easy to accidentally model the wrong thing. And that would be pretty embarrassing, wouldn't it? To like call up the president or call up like the CEO of your hospital and say, oh my God, we got a real emergency here. This disease, we've never seen anything like it. The probability of getting this cancer is 99.8%. And then, oh my God, we declare a national emergency, and then later it's determined, whoops, it's not 99.8%. You modeled the probability of not having the disease. Which means the probability of having it is that 0.2%. Big difference, right? So make sure you get that line right. We'll talk about the model fit statistics in next week's lecture. So for now, let's not worry about them. Although I think we will touch briefly on that -2 log likelihood thing there. But for now, let's just jump to where it says testing the global null hypothesis. So that's kind of like our overall F test from Stat 512. So that's our first starting point. We look at those, and that basically tells us, right, do we need to dig deeper, yes or no, right? If we reject the null hypothesis, that means at least one of our variables is useful in predicting the probability of getting a disease, which means, right, we need to dig deeper. Which variable is it? Is it one of them? If so, which one? Is it both of them? However, if we fail to reject, it's saying that none of our variables are useful, in which case we would stop our analysis. Now, of course, in any well-designed study, we would expect some sort of significance, but of course that doesn't have to happen. Now we'll talk about which of these we kind of will prefer. They all three are doing largely the same thing, and for larger data sets, they'll all be very, very, very close to one another. It's rare that they're going to lead you to different decisions. So, right, normally what I say is I look at all three, I say all three of them are basically saying I should reject the null hypothesis. So all three of these global tests are saying that at least one of my variables is significant. They all agree with one another, and typically that will be the case. And then here's that follow-up information that's necessary if we want to dig deeper. We have odds ratio estimates. We'll talk about those. We'll talk in a future lecture, I think in 2 weeks, about what's going on in that association of predicted probabilities. For now, let's just ignore that. And then our model equation is at the top. So our model equation, we have beta naught hat, that's the negative 0.7011. We have beta 1 hat, that's the 1.0731. We have beta 2 hat, that's the 0.8754. So we can use those to put together our model equation. We also have p-values, right? Doing type 3 significance tests, right? Is this variable adding anything above and beyond the other variables in my model? All right, so let's talk this through. So again, like I said, first thing you always do, check that line under response profile. Make sure that you're modeling what you intend to model. Then do your overall test of global significance. If they ever should disagree, it's generally suggested to use the one that says likelihood ratio test. We could talk very briefly about the likelihood ratio test. I don't want to get into too much detail because it actually it builds on like 506 type stuff, right? And 505 is not a prereq. Certainly 506 is not a prereq for this course. So I don't want to get too deep into it. But in 506, for those of you that have taken it, and that is the majority of you, in 506 you talked about something called a likelihood function, right? If you have independent data, f of x1, x2, x whatever, the likelihood function is that f of x1 times f of x2. Do you remember that thing? And because it's hard to work with these multiplicative models, right, we would often take the log of that, because the log of a product is the sum of the logs. And now when we're working with a sum, we could do things like take its derivative more easily. So you have this log likelihood function or likelihood function, right? The idea behind the likelihood function is it basically says like what is the probability or how likely is a parameter estimate to be, or actual parameter, how likely is it for an actual parameter to be a specific number given the data that we observed? That's the idea behind the likelihood function. You can compute a likelihood function, right, for any parameter estimate, and it would basically say, like, what is the likelihood, for example, that your probability is in fact 2%? What's the probability of pi being 2%, right, given the data that we just observed? And so the idea of kind of something called like maximum likelihood is that we actually want to find the one value of pi that has like the largest probability. That is, what's the value of pi that's most likely, right, given our observed data. So that's kind of this idea of a likelihood function. Briefly, I talked kind of this idea of why we work with a log of it, right? Because log puts us on this additive scale, which is easier to work with mathematically. Otherwise, the likelihood function itself is on this kind of multiplicative scale. Okay? And then the -2, it's starting to get a little bit theoretical at this point, so maybe just kind of leave that alone. It's just kind of a scaling parameter to kind of scale it. So what we do is we have this this log likelihood for our model of interest. We also have this log likelihood for a model that has no variables. So kind of what we're doing, right, big picture what we're doing, we're calculating some number, some value, this kind of abstract thing called a -2 log likelihood. We're calculating it for a model, our model of interest, the model we just fit, and we're also calculating it for a model that has no variables whatsoever. And the likelihood ratio test is comparing those. And so the larger the difference between these two numbers, the kind of stronger the evidence that the model we just fit is better than a model that has no variables at all, which of course is suggestive that at least one of our variables is useful in our model. That is, at least one of our variables is useful in estimating, right, the probability of whatever it is we're trying to model. Now, for a sufficiently large sample size, this likelihood ratio test can be shown to follow a chi-square distribution whose degrees of freedom are equal to the number of parameters in our model of interest minus the number of parameters in our variableless model. Now, the likelihood ratio test, part of why I'm kind of going into at least some depth regarding it, is it is a pretty important test, and it could be used in a more general sense. It could be used to do more than just this global test of overall significance. In fact, it can be used to do goodness of fit tests, which we'll talk about next class. And more generally, it can be used to compare any model that's nested inside of any other model. So basically, right, any model that's like a subset of another, you could compare them and basically ask yourself, right, is this additional complexity in the larger model adding anything above and beyond the simpler model? So we can actually verify the likelihood ratio test statistic reported by SAS. And we do that by getting the -2 log likelihood from our model fit statistics. And to do that, so there's two of those. There's an intercept only and an intercept and covariate. So the intercepted covariates is the likelihood ratio using all our variables. The intercept only is the one that uses none of our variables. The difference between those two is 9.1299, which is what's reported in the global test statistics. So go back to the output and see that for yourself. And the two models differ by two variables, right? The model we just fit has the sex and smoking variable, and of course we're comparing it to a variable that has no variables at all. So the difference between them is these two variables, and that's why if you look at the degrees of freedom are listed as 2. We are going to talk, and we're going to do other types of likelihood ratio tests. So I do want to kind of expose you to kind of the basic process here. So in terms of our data, all three tests are significant, indicating that at least one of our variables is useful in predicting the probability of having the disease. Now, if I wanted to write out the model equation, that's what it would look like. I think we kind of talked about that when I went over the output. Remember, the left-hand side is that logit function. We're not saying the probability is equal to that. We're not saying the odds are equal to that. We're saying the log odds are equal to that. Now remember, if I want odds ratios, we showed that that's as easy as exponentiating our parameter estimate. So, for example, the sex estimate was 1.0731. If you exponentiate that, do it yourself in your calculator, or pro tip, if you just type in exp parenthesis 1.0731 into your Google browser, Google will exponentiate it for you and tell you that it's 2.924. I do most of my math in my Chrome browser these days. And of course, how would I interpret that? I would interpret that as saying the odds of males having the disease is 2.924, that of females, assuming we're comparing smokers to smokers or non-smokers to non-smokers. And of course, we could also exponentiate the 0.8754 to get an odds ratio for smokers. Now, of course, SAS does this exponentiation for us. The odds ratios were already in our output, but again, I think it's instructive to verify. Builds muscle memory, right? In our biggest muscle of them all. Yeah, true physiological fact. What's the biggest muscle in the human body? The brain. You could, of course, if you want to, use those values, right, those things that we exponentiated, to come up with probabilities. So you can go back to the model equation and use that model equation to come up with probabilities. We do have formulas. Those probabilities are getting a little cumbersome. That said, I would consider it fair game on a test. So I would encourage you to maybe do one or two of these by hand. But it is tedious. I'm not going to pretend otherwise. And so, right, other than a test question that you want to prepare for, I would encourage you to use SAS to calculate the probabilities. Now we could think of these probabilities as kind of like predicted values. And so how did we output predicted values in Stat 512? We outputted predicted values using the output statement. So same here. Proc Logistic has an output statement. I want to name the data set that I want to create, so I'm creating an output data set. Call it whatever you want. I'm going to call it predicted. And there's a whole bunch of stuff that you can output, but I'm interested in outputting the predicted probabilities. So the keyword for doing that is pred. And I want to call that, I'm going to give it a variable name of probability. Notice, right here, I'm approaching that idea of what I want to model the probability of a little bit differently. So instead of using the descending option and the proc logistic line, this is actually my personal favorite way of doing it, because I could never remember, is it descending, is it ascending? I could never even remember what descending means or ascending means, at least not in the context of like how SAS picks what's being modeled. So I use this notation. You can put right next to your y variable in parentheses event equals, and then you can very explicitly tell SAS what you want to model the probability of. And that's the way that I prefer to approach it when I'm working on my own personal projects. And so here's my output data set. So the only thing that matters is the sex and smoke line. SAS will break that into two groups, those that had the disease and those that did not, which is why even though we only have 4 probabilities, the output data set has 8 lines because there's redundancies. Right? If you're female, non-smoker, then you're going to have the same predicted probability no matter which of those two groups you actually are, right, in practice. So what do? We just focus on the sex and smoking. So, right, female non-smokers have a 33% chance of getting the probability. So that's like your best case option. Man, this is a pretty prevalent disease, right? Your best case option is you have a 1 in 3 chance of getting it. If you're a female smoker, then it's a little bit worse. You got a 54% chance. If you're a male non-smoker, it's a little worse still, 59% chance. And of course, the worst thing you could possibly be for this particular disease in this particular imaginary world is a male smoker, in which case you have a almost 78% chance of having the disease. Now, I would encourage you to pull out some scratch paper and a calculator and hand calculate at least one of those probabilities. I definitely will ask it on a test. I may ask it on a homework. So, right, make sure that you get it right. And if you're having trouble getting your hand calculations to agree with SAS's output, of course, reach out and let me know. And so before we wrap up this example and kind of talk about a couple loose ends, right, we should of course be thinking, are both variables actually necessary for our model? Oh, I guess I didn't put that in a slide. Well, if you go back to the output, I think that you'll observe, and I'm blanking on which one, I think you'll observe that actually one of them is non-significant. So of course, right, best practice is still just like in 512. In fact, that's the beauty of logistic regression. The beauty of logistic regression is that we've taken this new novel situation and we've reframed it in a context where it's like 512. And by doing that, we can use all of the cool stuff from 512 that we've already learned, such as model building principles, which tell us if a variable is not significant, get rid of it, but also tell us things like, right, what interactions mean and how we can put those into our model, something we're going to talk about soon. And the other thing I want to talk about is what it looks like if we have continuous explanatory variables in a logistic regression model. So let's wrap up by talking about these two side topics. So the example we just did only had two explanatory variables, both of which were actually the simplest type of categorical variable, both of which were dichotomous. But I made the claim that if we put a continuous explanatory variable in there, SAS wouldn't blink an eye. SAS could care less. SAS would handle it just fine. And it would handle it in a very similar manner. So for example, imagine that we added age into our model, and imagine that SAS gave us a parameter estimate of 0.096. How would we interpret that? Well, the 0.096 does not really have an immediate interpretation. But if we exponentiated that, we do get an odds ratio. So how do you interpret an odds ratio with respect to a continuous numeric variable? In this case, we exponentiate, we get 1.1. How do we interpret that 1.1? We would say this. We would say for every 1 year increase in age, the odds of getting the disease increase by 10%. So the easiest way to interpret it is to convert that into a percent difference. But you could also say something along the lines of, I don't know, if you have two patients who are same with respect to all of their variables, they differ only in the fact that one is a year older than the other, then their odds of getting the disease is 1.1 times that of the younger patient. Now, often, right, we work in situations where like a difference of 1 unit is maybe not that meaningful, and so maybe we're interested in like 10 units or 100 units. When we're talking about age, it's actually pretty common to do units of 10 years, right? Because then we're like comparing 20-year-olds to 30-year-olds or 30-year-olds to 40-year-olds in like an applied clinical setting, right? When you're trying to kind of put together results that are applicable to a clinician, right? This is kind of the approach we take. And you can actually show that we can look at an odds ratio for patients separated by 10 years by actually just doing 10 times our coefficient and exponentiating that. So in this example, we would do 10 times 0.096, exponentiate that, verify in Chrome that that's 2.61. Maybe you could do it in Microsoft Edge. I don't know. Give it a try. Let me know. And so then we would say something like, right, for every 10 years you increase, or for every 10 years you age, the odds of getting the disease increase by 161%. Actually, when we kind of do it this way, it's almost like creating groups, and so it might even be actually it might sound more might sound better if we said something like you know, if you're comparing people, yeah, I think it's still going to sound a little awkward, right? Comparing people who differ only by 10 years of age. The older group is going to the odds of the older group having the disease is going to be 2.61 times that of the younger group. That one still sounded a little bit awkward. If you wanted to make a statement like people in their 30s, the odds of someone in their 30s having the disease is 2.61 times the odds of someone in their 20s. Again, assuming we're comparing males to males and smokers to smokers, right? All other variables held constant. We still have that little caveat when we're interpreting model coefficients in a larger multivariate model. So again, just like 512. We can also, instead of having to like do this little 10 times exponentiating, we can use a unit statement in SAS. So try playing around with that yourself, maybe with this data set. And if you do units age equals 10, then you should get that, then SAS will give you that 2.61. So the last thing for us to talk about before we finish up this lecture, just like in Stat 512, it's important to consider and test for the possibility of interaction amongst our explanatory variables. This means the same thing it meant in 512. So just like in 512, the presence of interaction means that the influence of one variable on the probability or odds or y depends upon another variable. For example, if there was interaction between smoking and race, it would mean that the odds ratio of smoking to non-smoking depends upon what sex you were born. It depends upon whether you were born male or born female. So just like in Stat 512, we can specify interactions in the model statement using the asterisk symbol. We could also use the same shortcut syntax. So for example, if we wanted to fit all possible interactions, say we have 4 explanatory variables, we want to fit all pairwise, all 3-way, and of course the one 4-way interaction, we could just do model y equals x1, that vertical bar x2, vertical bar x3, vertical bar x4.